Okay, hi Zach. Welcome to lesson number 81. If you're following along in your book, you can turn it to page 330 and you will be on this lesson. And it's a great lesson because it goes over graphical solutions and a couple of new terms, which are inconsistent equations and dependent equations. So we're going to find out in this video what that means, hopefully. It was a little bit of a hard lesson for me, so I hope it's not too hard for you. You'll probably get it right away, but it's a little bit tricky for me because, well, for one, I'm not as smart as you, and for two, I haven't done this in a really long time, and it was hard to remember this stuff. Okay, let's start out with this. I love the way the earth rotates. It really makes my day. Okay, pause for laughter, and we will continue and jump into the lesson, all right? So we're starting with 81A, graphical solutions. And this section of the lesson sort of gives us a little bit of a reminder on the degree of a term of a polynomial. Remember that? Remember how we were talking about the degree of a term of a polynomial? And basically to figure out its degree, like what kind of degree it gets, remember that? We sum up the exponents of the variables. So we sort of ignore the coefficients, ignore the coefficient numbers, but if it's a variable like x to the fourth or something like this, y to the fifth, and x, when there's an x with no exponent, remember basically the exponent is 1, and you add up the exponents on all the variables, not on these numbers, but just on the variables. And that gives you the degree, and guess what? That's you texting me, but that's okay. That'll give you the degree of the polynomial. Okay, so let's practice a few just to remember how to do it. So this term, 2xy to the fifth, is going to be a sixth degree term. And I call it a term just because it's only one expression. It's not like x plus x squared plus y, it's just one term, one expression. Okay, so if we have something like 4x, what is that? Well, that's going to be just a first degree term because whenever there's an x just like that, basically the exponent is 1. So when you add the exponents, all you get is 1. What about the one under it, xy? So if you're looking at xy, each of these has a little 1, and this turns out to be a second degree term. Okay? You starting to remember this? You're dusting off the recesses of your brain there and pulling out this information. All right, what if we're not talking about just a single term, but we're talking about the entire polynomial? If we're talking about the degree of the whole polynomial, then you have to scan across the whole polynomial and decide which term wins the prize, because only one term is going to win the prize for the whole polynomial, and then the degree that the polynomial gets is the term with the highest number. Does that make sense? Remember that? All right, so let's do a couple of these just to remember and dust off those memories, all right? So we'll start with this and this. This is the entire polynomial right here. So we're going to look at each term. This one has a 4 and a 1, so that's going to be a 5, okay? And this one just has a 1. So this is going to be a fifth degree polynomial, okay? Sweet. And then let's look at the next one. The next one, this is the entire polynomial right here. And we do include this x over there because it would be easy to just, subtract an x on that side and have it equal to 0, right? So it could be, it could be on any side of the equal sign. So we still have to look at all the terms. It looks like this term is going to be the winner, winner, chicken dinner. And that's going to be a 4 and a 1. So this one's also a fifth degree polynomial. It's the same as the one above. Okay, let's look at this last one. This is the whole polynomial right here. This one has a 1, this one has a 1, so they tie, and all you get is a first degree polynomial because it's a tie between those terms. All right, now, we also remember that what we've been talking about in a lot of these lessons recently are basically first degree polynomials with two unknowns, right? Because we've been talking about equations that look kind of like this. Y equals mx plus b, right? And when you have an equation that looks like this, it's a first degree polynomial because you've got a 1 here and you've got a 1 here on these variables. And you know that you're going to end up with a straight line. And you can graph that line based on the slope and the y-intercept, right? So these are called linear equations when it's just a first degree polynomial like that with two unknowns. And there are two ways to solve these straight line equations or these linear equations, and the two ways are called either the substitution method, like if you have two of these equations and you want to figure out like where they cross or where they have a coordinate in common, you can use the substitution method to remember what the other one is, the elimination, and this is when you add them together and you get rid of one of the terms. And you can also graph these. You can graph these lines or these equations. All right, now we're going to do example 81.1. First, we're going to look at this. Here's an example of a graph of a line. That's not a happy graph to see if you're talking about money. Are you saying my money's all gone? Okay, that would be pretty bad if Mr. Burns lost all his money. Example 81.1, we are going to solve by graphing. So basically, they want to solve this by graphing. What does that mean? What we've been doing is we've been solving by substitution or solving by elimination. But you can also find the xy coordinate that satisfies both of these equations if you graph each equation and then just look and see where they overlap. That would be another way to solve what's the x and y, where both of these, the x and the y could be part of this line and it could be part of this line, and you've got one x, one y. Let's just do it, and I think you'll understand what it means. Okay, so they want us to graph both those lines. So if we graph y equals x plus 1, let's see, how can we graph it? All right, so it says in the book, we can use two different methods for graphing the lines. First, you can plot points, so you can just like pick a random x and see what y it's going to be. Like for example, let's graph this first line in blue. Okay, so I'm going to put a box around it that's a dark blue. And let's pick a couple numbers for x and see what y is going to be. So if we put in the number 0 for x, and x would be 0 here, what would y be? Y would be 0 plus 1, so it's going to be 1. So it's this spot. So I know that this spot is on the blue line. Okay, I don't know if you saw, but I put a blue dot right there at 0, 1. So I just plugged in 0, 1, and that's part of this line. Okay, so let's do another one. Let's go a little bit further away. What if I put in the number 2 for x? So there's a 2 plus 1. Y would be 3. And then, bam, I've got another dot. Now, I also know because this is a first degree polynomial with two unknowns, that it's going to be a straight line and it's going to be linear. So all I need are those two dots, and now I can graph that line because I know that the line has to go between those two dots. And there you go, that's the line. So that's the line for this one. So we're done with that. Okay, now let's graph this next one, and let's do it in this like purple color, I guess. So that way we can see the difference. So now we're going to graph this one. You can also do it the same way, just pick a random number for x, or you can do this sort of the slope intercept line. And so let's do that. Let's do the slope intercept line so we do it a different way. So the slope intercept line, because this is the same as y equals mx plus b. Okay, so the b is where it crosses the y-axis. So that's this number here, which is 4. So I know that this line crosses the y-axis at 4, so I'm going to put a dot there. Then I know the slope of the line, which is rise over run. So rise over run means that I'm going to go -2. This is like -2 over 1. So it would be -2 over 1. So I know that this point is on that line as well. And then I know that it's a straight line because it's a linear equation. It has two unknowns, and so I can't draw a straight line apparently, but the machine can, my computer can. So I'll have it fix that. There we, still not, okay, there, I think I got it. Okay, close enough. Okay, so those are my two lines. This one is this one is y equals -2x plus 4, and the blue line is my y equals x plus 1. Now, it says to solve by graphing. So now we graphed them both. So now they want to know, like, where's the one spot where they both cross, which we can see. That was one of my dots, actually. And it crosses at 1, 2. So at 1, 2, that's my x and y coordinate where they cross. So I know that x is equal to 1, y is equal to 2. And that's where those numbers right here satisfy both of those equations. And you can check your work by plugging them into these original equations right here. You can check it by plugging those numbers into these original equations. And if you do that, you will get something that is true. If you get something that is true, then you know you did it right. Okay, so let's try it. So let's see. One of the equations is y equals x plus 1. So if I plug in 1, 2, this is my x, this is my y. So I'm going to plug in the 1 for the x, so then I'll have 1 plus 1 on this side. And for my y, I'm going to have the number 2. 2 equals 1 plus 1. Is that true? Yes, so I did it right. Let's check it with the other equation too. Okay, so the other equation was y equals -2x plus 4. Y equals -2x plus 4. Now, what are my numbers again? They're right here. X and y is 1 and 2. So I'm going to plug in a 1 for the number x. 1 times -2 plus 4. And what do I put in for y? I get 2. So 2 is equal to -2 plus 4, which is equal to 4 minus 2. Is that true? 4 minus 2 equals 2? Yes, so that's another true statement. So if I get those true statements, then I know for sure that these coordinates, 1 and 2, x is 1, y is 2, that is the solution for both of those equations, and that means those two equations are lines and they cross right at that point, which is cool, huh? That's pretty cool. Let's do another one because that was so fun. And this has to do with just graphing. Is it linear or is it accelerating? Accelerating lines are not a straight line. They look more like that. So is that growth linear or accelerating? And she says accelerating. Oh, maybe we can graph it out. What? It looks like two nerds are getting married right there. So yay for them, huh? All right, so let's do example 81.2. And it says solve by graphing. And these are the two equations. Y equals 2 and y equals x. Now don't be confused by y equals x. I mean, they're just two different lines. So here's the plot where we're going to do it. So let's use what color should we use? How about a green? Let's do y equals 2 in green. So where would that be? That basically is saying that no matter what you put in for x, along this, like you can pick any x, like 6, it's always going to be 6, 2, 4, 2, 2, 2, right? So -2, 2. So no matter what you pick, the y is always going to be 2. So that line, y equals 2, looks like this. This is easy peasy. So this is y equals 2. Okay, let's do the next one. Y equals x. What is that line going to look like? And let's do it in like this bright blue. So y equals x. So what that means is no matter what you pick for x, like let's say you pick 1, y is going to be 1. Y is the copycat here. So if you pick 2 for x, y is going to be 2. What a copycat, huh? If you pick -1 for x, then y would be also -1. So if it's a copycat situation like that, where y is equal to x, then that line is going to look like, I can't draw a straight line. It's going to look like this when it's positive, and this, yeah, like that when it's negative. So this is the line y is equal to x. No matter what you pick for x, y is the copycat. Okay, so now they want to know what's the solution, meaning where do these lines cross? And I think you can see that they cross right here at 2, 2, which makes sense because y has to be equal to 2 always for that green line. And the only place where y is 2 with the other line is the same place where x is 2 because it's a copycat. So the answer, the solution is 2, 2. That means x is 2 and y is 2, and that's the solution. So if we substitute, just to make sure that we're doing things right, let's put in y is going to be 2 equals 2. That's true. And what about this one? If we plug in 2 and 2, we get 2 equals 2, and that's also true. So we got 2 true statements. That means we did it right, and that means this is the correct solution. Easy peasy, right? All right, let's do another one. All right, you're getting the hang of this now, right? You're probably feeling confident, like, let's do this. Yeah. But you know these examples just get harder and harder. Okay, they want us to solve this one by graphing. So we have these two equations. We have y is equal to x plus 2 and y is equal to x minus 1. They're linear. It's a first degree polynomial. I know they're going to be straight lines. So I know those things just when I first see the equation. So how should we solve this one? You could do y equals mx plus b. Let's graph them that way. Okay, so for this first one, the b is 2, so that means it crosses the y-intercept at 2, so I'm going to put a red dot right there. Right there. Okay, and then what's the slope? The slope is 1 over 1, so that means rise over run. Rise over run is always going to be 1, 1, 1, 1. So that means it's going to be this line. Yeah, that is the line. So I'm going to draw that in red. Okay, let's see if I can do this. Not very straight. Nope, that didn't work. Let me try that again. Come on, erase. Erase my line. Erase my crooked line. How about this? Did that straighten it? No, for some reason. You know what though? It's close enough. I think it's close enough. All right, so this is my y equals x plus 2 line. Okay, let's do the next line in like a bright blue. So y is equal to x minus 1. So y equals, this is my m, 1 over 1, and this is y equals mx plus b. So it crosses the y at -1, so that's here. So I'm going to put my blue dot there. And my slope, once again, is rise over run is 1 over 1, 1 over 1, 1 over 1. So that means this is on it, this is on it, this is on it. All those dots were on it. So, okay, I see what's happening here. Let's check this out. Check this out. You have 2 parallel lines. So this is y equals x minus 1. Okay, that's one of the lines. and then you have y equals x plus 2, and they're going to be parallel lines because their slope is the same, and they're never going to meet. So what's the solution? The solution is these are parallel lines, parallel, and they never meet. There is no x and y that is on both lines. And so this is what's called an inconsistent equation. Inconsistent equation. And that means they're parallel lines, they never meet. There's no solution that you can figure out that's on both of the lines. So let's look at this a little more. These lines are parallel. They will never intersect. That means they will never meet each other. There is no point that is on both of those lines, and that is called an inconsistent equation. So you have to know that term, and you have to know when it's an inconsistent equation. We're going to look at that a little bit more, but there's no number that I can put in. I can't plug in an x and y. If I were to plug in an x and y, you would get a false statement. I was going to say a not true statement. You would get like 2 is equal to 4 or something crazy like that. It would not work because those are inconsistent equations. All right, we're going to look at that a little more closely. Inconsistent equations, that's the next section. All right, so 81.b, if you look on page 332, it goes over these inconsistent equations. And basically, they have no common solution. Like they each have a solution. Here's an example. You have x plus y equals 2 represented by this red line right here. Okay, and then you have x plus y equals -3 represented by this blue line right here. And again, they're parallel. They're always the same distance apart. And so if they're always the same distance apart, then they're never going to meet. That means there's no common solution. All right, so let's see. From the figure, we see that the lines appear to be parallel. They don't intersect. If they don't intersect, you can't find an x and a y that would work for both equations. And if you try like doing that, right, because there are ways to try, remember? They're called the substitution method, substitution, and what's the other one? Elimination. Elimination. Let's say we were to try substitution or elimination when you've got inconsistent equations. Well, let's try it. You will get a false numerical statement. So we're going to try it. These are the two equations right here. I wrote them down. X plus y is 2 and x plus y is -3. Let's try substitution. So for substitution, let's put in, for this, instead of this x, let's solve this one for x. Let's solve this equation for x. So this is going to be x equals -3 minus y. Okay, so now we've got a number for x. I'm going to plug this in here. Okay, so I'm going to get -3 minus y. I'm plugging it into right here. Plus y equals 2. So I've got -3 minus y plus y just cancels out. So I can just erase that. And then I have -3 equals 2. Is that true or false? It's definitely false. And when it's false, I know that there's no x and y that is going to work for both equations. You just cannot do it. Let's try it with the elimination method now. Elimination. Okay, so here are my two equations. Was this the original? No, the original was x plus y is 2. X plus y equals 2. And then the other original was this one. Okay, but they multiplied everything by a -1. That way the y's are going to be eliminated. Okay, and so when you eliminate the y's, you add these two together. Do you get it so far? Okay, So when you add them together, you get, let's see, x minus x is 0. Y minus y is 0. 0 plus 0 on this side. And you get -2 plus a -3, which is -5. So is 0 equal to -5? That is false. So if it's false, then there's no point that satisfies both equations. Okay, cool. So we figured that out. Let's do example 81.4. And it says, do the following have a common solution? So now they're not telling you, this is a teaser. Are these parallel lines or are they not parallel lines? Okay, so we don't know because they're not graphed out, but let's just do like the substitution method and see if we can figure out if they have a common solution. So this one is already solved for y. Actually, this one's already solved for y too, but let's take this one, plug it in for that y. Okay, so then we'll have, yeah, I can use that. X minus 1 is equal to x plus 2. Let's add 1 to both sides, add 1 to both sides. And I have x is equal to x plus 3. How can I get rid of the x's? Did I do this right? How can I get rid of the... Oh yeah, just subtract an x. Subtract an x, subtract an x. So x minus x is going to be 0 equals 0 plus 3. 0 equals 3? No, that failed. So that's false. Okay, so if that's false, then that means the original equations have no common solution. No common solution. That means they must be parallel lines. So cool. All right, so those were inconsistent equations. Now let's go over dependent equations. Okay, so we have defined in the past equivalent equations. So I'm just going to remind you really quick about that. Equivalent is when you take an equation like x plus, let's do like x plus y is 1. And if you multiply everything by 2, it would be 2x plus 2y equals 2. And those equations are basically the same equation. You're not changing the value of anything. You just use the Dunning-Kruger rule and you multiplied everything by the same number. So those are called equivalent equations, and that's the definition of that. Okay? So if they give you something that turns out to be basically the same equation of another one and you graph them both, you'll get the same line. And that's kind of what they're talking about here with dependent equations. So here we go. We're going to graph y minus x is equal to 2. Actually, they've done that for us in the book, and that is this line. Y minus x is equal to 2. Okay? Now, if you multiply everything here by 2, what do you get? You get this equation, which is 2y minus 2x is equal to 4. Now, if you were to graph this one and just put in like a random number for x and see what you get for y, then you would get the same exact line because these equations are equivalent. And there's actually an infinity number of ordered pairs where x and y, so what about x and y? Like, can you find a spot where x and y satisfies both of these? Yeah, it's going to be the same spot everywhere because it's on the same freaking line. So there's an infinite number, right? So if you have like x is, I don't know, x is 0 and y is 2, so 0, 2. That solves this equation, but it also solves this equation, and it will every time, no matter what you pick for x, if you plug in the y, you'll get the same y here as you do here. So I've said that a couple different ways, so hopefully you get it. And that means that they're equivalent linear equations, and that also means they're dependent equations. So equivalent linear equations are just called dependent equations. Okay, and you could multiply this by 2 to get this one, but you could also multiply this by 3, and that would be another dependent equation. You could multiply it by a half, and that would be another dependent equation, or you could multiply it by the square root of 2 or x or 1 over x or anything, and you will get another dependent equation. So when you graph it and it's the same line, then you know it's dependent. Okay, those lines are so dependent on each other that they're overlapping. Think about it that way, okay? So let's do example 81.5 to make sure that we understand this. Determine if these equations are dependent. Remember, they're so dependent on each other that they are basically overlapping lines. So we've got this equation, and these are the ones that we graphed earlier. So we kind of already know that they're dependent, but let's prove it mathematically. And the way that we prove it mathematically is we use either the substitution method or the elimination method. So let's start with the substitution method. All right, these are my two equations. So let's solve this first one for y, because it looks like that'll be easy to do. Y is equal to 2 plus x. And then we're going to take this and plug it in for this y. Okay, so then we'll get 2 plus x minus 2x equals 4. And if I multiply this out, 2 times 2 and then 2 times x, it's going to be 4 plus 2x minus 2x equals 4. Plus 2x minus 2x cancels out those terms because you've got 2x minus 2x. So it's just going to be 4 is equal to 4, and that's true. And so that's a true statement. So that's what happens when you have dependent equations. You just get these two numbers. There's no variables anymore, and the statement is true. Okay, let's do it with the elimination method. So here's the elimination method, and here's the two equations again. These are the same ones as before. They're just like pretending we don't know what those graphs look like. So the elimination method means we're going to try and add these together in a way that makes one of the terms cancel out. So we could get the x's to cancel out if we put like a 2 here, right? So let's multiply this whole thing by 2. So if we multiply that whole thing by 2, we get 2y minus 2x equals 4. And then if we add, we would have to multiply it by a negative 2. So negative, make that a positive, make that a negative. Okay, so now when we add, we get negative 2y plus 2y, that's 0. Positive 2x minus 2x, that's also 0. 0 plus 0 equals 0. And so you have 0 equals 0. Is that true? Yes, of course it's true. 0 equals 0. So that means that we get a true statement and all the variables are gone. That means that anything that you pick for x and y, as long as it satisfies one of the equations, it's going to for sure satisfy the other equation. And that means that these are indeed dependent. Dependent or ent? Dependent. Okay, cool. All right, so let's summarize. He thinks that pretty much sums it up. I could get one that says world's best teacher. I should buy that for myself. Yes, I'm going to sum it up that way. World's best teacher. If we have two linear equations and two unknowns, then you know that those equations are either going to be one of three things. They can be consistent equations, and a consistent equation, when you graph them, it's going to look like, well, you're going to have one line here, and then you're going to have another line here, and you're going to have some point, that they have in common. That's a consistent equation. That's what it looks like. Okay? Sweet. Now, what it could also be an inconsistent equation. Inconsistent equation means you have two parallel lines. That means that those lines will never meet. I didn't draw it very good, but that's okay. They never meet, so there's no common solution, and they are parallel lines. That's inconsistent. So that I'm going to write in between the lines, inconsistent, because they never meet. That's sad. It's kind of sad. They have so much in common, and they never meet. All right, what's the last one? It's a dependent equation. A dependent equation means you've got the same line. So that's one of the lines, and this is the other line. And if I'd have drawn it better, you could see that they're the exact same line, and that's called a dependent equation. So if you've got a linear equation, two linear equations, two unknowns, it's going to be one of three things. It's going to be consistent or inconsistent or dependent. And now you know what all of those mean. Sweet, sweet. One more example, and this lesson is over. Okay, and we are back, and we are going to look at this example 81.6. This is the last one. Alrighty, so here's what we're going to do. They want to know whether these equations are consistent or inconsistent, which means they have no point in common, so they have to be parallel lines, or are they dependent, which is basically just one line on top of another. I don't think it's that, because it doesn't look like you can get one to equal the other one if you just multiply by something, but that's okay. So it's probably going to be one of those first two. So let's solve this, and you can decide whether you want to do it with the substitution method, elimination method, or the graphing method. And to me, as I look at these equations, I see that this is going to be easy to substitute x in and just plug it in there for y. So I'm going to use the substitution equation, but you could use substitution, elimination, or a graphing method, okay? So if I use the substitution method, this is the easiest way it looks like to y is equal to x. So I could just cross out that y and put x is equal to that and see if I get a true statement or a false statement or, you know, whatever. So let's put in y equals 2x plus 5, and then I'm going to substitute for this one, y is equal to x, so it's going to be x is equal to 2x plus 5. Now if I let's subtract 2x minus 2x. X minus 2x is negative 1x, so just negative x is equal to 5, and that means x is equal to negative 5. Okay, so that means x is equal to negative 5. That gave me a point. So out of all of those things, I could have had a true statement like negative 5 is equal to negative 5. If I would have got that, it would be something different, right? It would be the dependent equation maybe, but I got just a point. Okay, so I got this point of x is equal to negative 5. So if that's x, then what is y? So if x is equal to negative 5, let's go back and look at the equations. If x is equal to negative 5, that means y has to be equal to negative 5. So my point is negative 5, negative 5. And that's the only answer. So that means that if you graph them, it's going to look like two lines, and the place where they cross is negative 5, negative 5. So that means that they are consistent equations. Okay, hopefully that's not too confusing for you, but do your homework and see how you do on it, and let me know if you have any questions. Okay, love you, Zach. Good luck. Bye.